or a result?
Failure is both.
Okay.
Failure encompasses everything within this. All right? So, that is my opinion. Like I said again, how many times have you seen failure written in the textbook? Zero. Okay? They don't mention the failures. They say, oh, well, that just didn't happen. You look at published journals, Nature, Science, two of the biggest scientific research articles out there, or journals out there. How often do they report failures? Never. Okay? Do failures teach us something? Yes. Okay? They are very, very important to our learning and our understanding of the material and allow us to advance. Okay? The trick is to learn from our failures so that we can move forward. Okay? So you have to remember that failure is an integral part of this. Okay? And as we already discussed on whatever it was, Tuesday, okay, when are we supposed to fail for this class? Fair enough, often.
On the homework.
On the homework. And another place that's reasonable to fail. Please don't fail on the tests. Okay? I mean, it happens, but you can fail on the tests. Quizzes is an option. Where do quizzes happen? In lecture. Okay? We will all fail in lecture. I will too. Okay? I can't add. I can't multiply. I can't divide. You'll notice that I cheat, and every so often I hide answers somewhere on the slide so that I don't have to think about it. Okay? So we will fail. We have to accept that, use that as a learning lesson to move forward. Okay? We already talked about that. So now, after all of that fun work, we've immediately jumped into Chapter 3. You'll notice that we've skipped PSS, or the PSS chapter or section, if you will, and Chapter 2. We'll come back to that. We want to talk a little bit about matter first, because that's kind of important. Remember, we do have the syllabus quiz, and we do have that quiz number 2. Okay, you'll notice that scores haven't gone up for quiz number 2 yet, because I'm kind of waiting until I have time at the end of the week. Okay? But in theory, on Friday, I'll start posting scores for sending me that email. So, what is matter? Okay? Well, a lot of this is going to come down to observation. Okay? We're going to have two types of observation, qualitative and quantitative. Okay? All science is based around these two. Okay? Some people are better at one observation than the other. I personally am all qualitative. I'm pretty bad at quantitative. Okay? I can fudge my way through it and people think I can teach it, so that works. Okay? But qualitative is my primary focus. Okay? What is the difference between those two? Okay, we've talked about a couple times what I'm horrible at. We've said that's quantitative. What do you think? It's actually less, I mean, both of them are data. Okay, so you need a little bit more than just data.
Quantitative is how much, numbers-wise?
Amounts. Okay, so yeah, a bunch of people shouted out over here. That's cool. That's fine. We got numbers and we got math. Okay, that's our quantitative. Lots of numbers. Math usually comes into that. We can push that even further. We get units. Okay, all of which we'll talk about. What is qualitative?
Visual observation.
It's just our observation. Okay. And it's typically a visual observation, because we can still think of our quantitative as visual. We're going to weigh something. You step on a scale. Okay? There's a visual observation of what that scale is saying. It gives you some numbers. Those numbers are the quantitative observation. Okay? The qualitative observation is, I need to lose some weight. Okay? Two separate things. Okay? Ideas or questions on that? Kind of makes sense? Anybody get the title, just because these are fun?
Yes.
What's the matter? Because we're talking about matter with you? Ha ha ha. Right? Okay. I like to call these Easter eggs. You don't have to get them. You don't have to laugh at them. It's quite all right. Okay? But they will pop up every so often. So, qualitative observations. Let's start there. Okay? And as soon as we start with a qualitative observation, the very first question I ask brings in numbers, quantitative. Oh, that was nice. Okay. What is 70-80% of the composition of life? Water. Water is our primary discoverer. That's where a lot of our science has centered around. What you will find is in general chemistry, virtually everything you do has water involved in it. Okay. Is that the only form of chemistry? No, we can do a whole bunch of other things that move outside of water as our general observable, okay, or as our carrier. Water has some special properties associated with it, which is why it's been our primary carrier. Any ideas what those special properties might be? Come up with a different idea. Any idea what different types of matter there are? I know it's a really vague question. We'll see if you give me the answer I was looking for. You can give me a bunch of correct answers too.
Liquid.
There we go. Liquids. What other forms of matter are there?
Gas.
Gas.
Water has all.
Solid. Thankfully no one said plasma. Thank you. Okay. So we've got these primary phases of matter. Why is water such an interesting compound? It gives us all three of these phases. Okay. Depending on where we're located on the planet, we can see both or observe gaseous water, liquid water, and solid water. Okay. That's kind of neat. Where do we see those? We get cold enough, we get snow or ice. Okay. Then, of course, the second picture. What do I end up showing? A whole bunch of snow and ice, but liquid water. Okay. And then gaseous water. How do we see gaseous water? That becomes a little bit harder, but what happens when we heat up liquid water? Eventually, what happens to it? It seems to disappear. It disappears into our air, but we could collect that air and get the water back. So there has to be another phase because that species isn't just disappearing. It's becoming invisible to our eye, but we can bring it back out of that nothingness. So there has to be some phase for that nothingness.
Condensation.
Okay. Which is our gaseous phase. Okay. When we look at condensation and other terms that float with that. So we've got solids, liquids, and gases. What are some common observables that we could come out of these? Okay. Something that we could compare all the way through. Okay. Your textbook addresses these. Shape, volume, and compressibility for all of these. For a solid, what can you describe about its shape? Okay. If you think kind of long term, we could compare solid to liquid to gas, their shapes.
It's fixed.
It's fixed. Our shape cannot change. Okay? If I take a solid, it stays in that shape. I can then force it into a different shape, but then what happens? It stays in that shape. So our shape for our solid is fixed. It cannot change. What happens with the liquid? If I take my liquid and pour it into a beaker, it now conforms to the shape of the beaker. If I take that same liquid and I pour it into the table, okay, the liquid takes the shape of the table and falls off of it. Okay? So what does that mean about the shape for our liquids? It's variable. And our gases? Also variable. What about our volume? What happens for a solid? Okay. Let's avoid the greater or less than, because that argument, depending on the substance, can get all sorts of messy on us. It's fixed. Okay? For an individual solid, it doesn't matter if I change its shape. The volume, the space that that solid occupies, is the same in total. Okay? Which means its volume is fixed. What about the volume for a liquid? It's also fixed. Okay? It may take a different shape, but it's still going to form that same volume. And a gas? It is variable. Okay? I can take a balloon and blow a bunch of gas into it. Okay? And I tie that off. Okay? Can I change the volume of that balloon? I can squeeze down on that balloon. I still have gas in there, but I've changed the volume. Our volume is variable. Compressibility. What does compressibility mean? How much it can be squished. So what we're looking at is a change in volume. So in the case of a gas where I can change the volume, what happens to my compressibility? I'm going to have a significant amount of compressibility. We'll just call that significant. Uh-oh. Is that spelled right? That's good. Let's just move on. How about for a liquid or a solid? Okay. What happens to ice when you compress it? Does it move? It breaks. It shatters. Why? Because it can't compress. Okay? So it's very, in this case, we're going to call it, oh man, I had to pick another hard word.
Negligible?
Negligible. I get that one right too? Oh, you're shaking your head.
Oh.
Also not an English major. Okay. What about our liquids? Take a beaker full of water and you stick your hand to compress that liquid. What happens? Your hand goes through it. The water just displaces around your hand. Okay. Are you compressing the water at all? Nope. Also, not a lot. Man, you guys are so critical. Okay. So we've got some kind of basic features that come out of our different phases of matter. Okay. So we've got these different things that we can observe. Okay. And that's ultimately what scientists were initially doing. They picked different compounds or different objects and they tried to classify them as quickly as they could. Solid, liquid, gas is a nice way to classify those. Right? And they tried to learn more about each of those individual phases and materials. Right? So while matter has all these phases, each of those phases can then be subcategorized into mixtures or pure substances. Okay? Did a slight edit on this, which I think was actually posted, but maybe it wasn't. Mixtures. Okay? What's happening with a mixture is we're taking multiple things, and those multiple things are near each other. Spatially near each other. I'm trying to avoid the term physically, okay, because that brings in physics. We don't deal with physics. Okay, what we're talking about is spatially, I've got a bunch of different things that are near each other. What happens with a pure substance? Okay, well, now I'm still having a bunch of things, but those bunch of things are chemically linked to each other. Okay? What is chemically linked? Well, if this is your first chemistry class, I'm using the name of the class to define a term. Well, you're taking the class because you don't know what the term means. That doesn't really work very well. Okay? So part of this class is going back into detail of what this chemically linked means. Okay? Mixtures, okay, can further subdivide into two categories. We get heterogeneous and we get homogeneous. In heterogeneous, we see a visible separation between these. What might be an example of a heterogeneous mixture? So we'll start with the first one I heard, sand. What's the visible separation in sand? What's our mixture? Okay. It's a harder example to work with, but it does work.
That's separated.
Yeah. So sand, we do have different minerals. Okay, so if you took a fistful of sand up and you looked at it really, really, really closely, you might see that there's bits of shell versus bits of crystalline-looking things. Okay, so it is officially a mixture. It's not the easiest one to see, but it does work as a mixture. Okay, minerals, let's just say minerals in shells. The other one that I was hoping for was a little bit easier. Water and oil. Okay. So if we take oil and we mix it with water, what happens? They stay separated. There is a visible separation between those two. Even though spatially, right on the interface where the water and the oil interact, okay, there is a spatial alignment. They are next to each other. Okay? But there is a visible separation between them. Kind of make sense? So let's push it to the next example that someone tossed out there. And I guess I'll leave those up for the moment. Whoops. I'm going to ignore that arrow for the moment. Pretend I didn't draw that. I think I heard somebody say this. What phase is salt? Solid. What phase is water? Liquid. Okay. Different phases, that could be a heterogeneous mixture. So if we think about sand, we added sand to water. They are spatially next to each other. We look at the ocean, okay, or at the beach. They do exist, if you haven't been there. Water, sand, spatially they are right next to each other. Okay? But we can visibly see a difference. So solids and liquids, we could potentially put into this heterogeneous system. But what happens when we now add salt to water? That solid salt disappears, if you will. Okay, we can use the proper term dissolves into the water. Can you see any more solid salt? No. Okay. Is the salt all collected in one section of the water? Okay. For instance, if I stuck a straw into that beaker that had water and salt in it, and we mixed everything, okay, and we can even give it some time to settle out. I stick the straw in the very top of the water, and I taste that water. What does it taste like? Salty water. I stick that straw in the very bottom of the beaker. What's it taste like? Middle of the beaker. Outside the beaker. No, just testing. Okay. The salt is completely evenly mixed to the water. There is no visible way to tell the difference, and I also can't even taste a difference. At all points, the water tastes like salt. Okay. That cannot be a heterogeneous mixture anymore. We don't have those separate phases. So instead, we have no visible separation, and what we have in the case of water and salt, a homogeneous mixture. Okay? Questions? Let's push over to our pure substance. We're looking at chemically linked. I'm going to erase everything now, get some more space. That gets separated into two sections, compounds and elements. Okay. Elements are the basic building block for chemistry. Okay. What we're looking at in an element is there is only one type of that element, for lack of a better word, but there may be thousands of those individual pieces, if you will, in that container. When we move to compounds, compounds are a combination of at least two elements and typically classified of different types of elements. Okay? So what could be an example of either of those? Sodium chloride is an example of salt, fair, compound or element. We're looking at a compound. Okay, and we could write that out as sodium chloride, or we could write out the symbols. How do we know what the symbols are? Okay, where on the periodic table does it say sodium? It doesn't say it up there, right? Okay. Sodium is not a combination. Sodium is just that Na. Can we find Na up there? Yeah. Where does it say sodium? Ooh, doesn't. Okay. You're going to have to eventually tie the name of the compound or the name of the element to its symbol. Okay? And we will probably talk about that today. All right. And if we look for the Cl, we see Cl up there too. So what we're looking at in the case of this compound is that we've taken two elements and we've combined them with each other. Okay? What if we now shift to it being just elements? Well, I could say, well, I just want to look at sodium. There we go. Now we have an element. Sodium, all by itself. Okay. Conveniently enough, you guys picked a good example on this. Let's look at the other element, chlorine. So we could write the element for chlorine. Anybody know the symbol? Close. Cl2. Yes, technically it is a gas that does not necessarily tie with this, though. Compound or element? Yes, that was a good answer.
Molecule.
Okay. Molecule is yet another way of referencing compounds to a certain extent. They're almost the same thing. Okay. Is Cl2 a compound or an element? Really kind of straddles the barrier between this. So this is our first example of the lack of black and white within science. Okay. What is compound? Well, a compound is something that we put out as a definition. That didn't just come down from the heavens and say, this is a compound. We said that is a compound. We said that is an element. And we came up with rules to define them as best we could. Are there examples where we come up with something that straddles the two definitions? Yes. More typically, when we're looking at compounds, it's at least two different elements. So when we look at the formula Cl2, that 2 means there are two chlorines. Well, is a chlorine atom different from a chlorine atom? No. So we don't satisfy the different aspect of the compound, and we tend to classify that as an element. Cl2 is one of the special exceptions, and what we have is something referred to as its elemental state. So even in the name of it, we're referencing it as it being an element. Okay. Could we classify it also as a compound? Yeah, kind of, because it is two elements, okay, or two pieces, but they aren't technically different. So Cl2 happens to kind of straddle that barrier. More typically where it's classified is under the element title. Okay? Kind of, sort of? Yes.
So that'd be the same with hydrogen.
That would be the same with hydrogen, since you brought it up. Hydrogen, anybody else know one?
Carbon.
Not carbon, unfortunately.
Is it all the red ones?
Oxygen.
Oxygen's one. That might be a possibility, so keep trying to shout them out and see what happens.
Iodine?
Yeah, so too.
Iodine. Oops, there goes the red one option.
Helium?
Helium's not one. There goes our red option again. Okay, do I have three? Was it hydrogen, iodine, oxygen,
Chlorine
chlorine,
or fluorine?
fluorine? Well, you got two for that one. Bromine, nitrogen. How many different elements? There are 7. 7 elements hold this diatomic, or sorry, this 2-atom classification. Let's walk through them again. It was hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. What's that shape? 7. Okay, so it's 7 plus that extra 7. Okay, so there are 7 total elements that are diatomic. Our shape only gets us 6. So that extra one is our hydrogen as our diatomic. Are there other elements that can pull off similar things? Yes. Sulfur typically forms as an octamer, meaning it has 8. There are 8 sulfur atoms all linked to each other. Okay. Are you responsible for that one? No. And we're not officially responsible for the diatomic one yet, but you opened that can of worms, not me. Okay, we'll see that later this semester. Questions on that?
So is that because they're not stable as one?
We can look at it as a stability argument, and that opens way more worms than I'm even going to start to talk about yet.
Okay.
Hi. So, our first subcategorization that comes out of this is we can run into metals, metalloids, and nonmetals. So we've got a list, two lists, left and right. Okay. What do you think those two lists correspond to? There are two lists, so if you say metal, I kind of agree with that. What do you mean? Which list corresponds to metals?
The one on the left.
One on the left. How do you know that?
Conduct heat, electricity.
So some of you may remember this whole conducting electricity thing.
No.
What runs through our walls? Copper, which is a metal. Most people seem to remember copper as a metal. Okay. And it also conducts electricity. You'll notice on the rightmost list, it says nothing about conducting electricity. In fact, it says it does not conduct electricity. So with our first example of an element we're aware of, copper conducting electricity and copper being a metal, most of our metals fall on that leftmost category. All of those traits tend to hold true. Where are our metals on the periodic table? Because it might be nice that theoretically the periodic table was organized to allow us to find this information quickly and easily. So we said copper is a metal. Anybody know the symbol for copper? I pointed over here. Cu, which is 29. Anybody know any other metals?
Gold.
Gold, which is?
AU.
Au.
Tungsten.
Tungsten, symbol.
Delete.
Anybody know any other metals? Silver. Okay, stop. Okay. That trend. Let's hold up. Well, you guys went too fast on me. Okay, where did we find all of those elements that we just listed so far? We found them in the middle. Is there anywhere else? Turns out that very few metals show up on the far right, and everything to the far left is classified as a metal. Okay? So our metals are pretty much leftmost on the periodic table. So we can pick out anything on the left side of the periodic table, and they will match these characteristics. Kind of neat. They'll match most of it. What about our nonmetals? Whoops, let's try that again. What is the other list supposed to represent? We've got our nonmetals. Okay. Anybody know the element name for a nonmetal? You may not, it's fine.
Potassium?
Potassium is actually a metal with K on the far left.
Helium?
Helium is a nonmetal. Okay, so what we could try and do is pull through our list here and see if we know any of the others. Okay, we see solids and gases. Does anybody know a gas?
Radon.
Okay, radon. Others. Argon. That sort of works. Oxygen. Nitrogen. Helium. Oxygen O, nitrogen N, helium He. Where are all of those elements showing up on our periodic table? The far right. Okay. All of our nonmetals align on the far right of the periodic table. And they tend to all have these same basic characteristics. A lot of them tend to be gases, but some of them pick up as solids. They tend to be dull. It's your classic dull example of a nonmetal. You light a fire, you start burning some wood, and it turns into? Charcoal. What is charcoal made of? Carbon. That dull color that you're seeing on those leftover charcoal remnants is the color of carbon. Okay, so it's not very shiny. What happens if you hit that with a hammer? It shatters. What happens if you hit gold with a hammer? It just bends. So we're looking at malleability versus brittle. Okay, if we tried to put carbon in our walls to pass electric current, does it work? No, it doesn't work very well at all. Okay, that's why we don't use carbon, we use copper. Okay. We can look at densities, melting points. Okay. We also tend to see a reaction pop up here, a reaction difference. Our metals tend to react with nonmetals, not so much with other metals. Our nonmetals, crazy little things, okay, react with pretty much everything. Okay? So, next push. Picture at the top. Those metals or nonmetals?
Both. Non.
Okay. Solids, or not solids? Solids. That one's a bit dicey. Luster. What is that word? Shiny. How many of those are shiny? Ooh, all of them. Malleability. How many of those are malleable? Good call. Conducts heat or electricity? High density. Okay. The only thing we've got to work with are those first two. Solids and does it shine? Based on that information, what are we looking at up here? Probably looking at metals. Good guess. They're all metals. How about these guys? Okay. These are our nonmetals. Okay. Some of them are more obvious than others, and it gets a little bit difficult. We run into an issue with gases. Looking at a picture of a gas, how easy is that? Doesn't work out so well. So what's going on in this middle one? Purple one. It's neon. What happened is we took trapped gas and we excited it. Okay? That then gives off a nice bright color. Kind of neat. Okay, we'll talk about that later in the semester. The other one's fun. What about that brown one, brown yellowy one in the middle? What's happening there? What phases do you see in that? We got a liquid and a gas. There's actually two phases there. This belongs to one of our interesting elements, bromine. It happens to be a liquid at room temperature. Okay, so that's the other fun thing with this. When we define our different phases, it's all based off of temperature. So when we're looking at our phases of metals, metalloids, and nonmetals, we're saying roughly room temperature, what is the phase we see? With bromine, it's a liquid. Take a look at the lists. For metals, we say most solids. So it's a liquid, it can't be a metal. Nonmetals? Solids or gases. Well, it doesn't say anything about liquids. There we go. Careful reading. It says most. Okay. Why does it say most for both? Well, bromine is a nonmetal, which happens to be a liquid. What's the metal that's a liquid? Mercury. Where is mercury on the periodic table? Symbol? Hg in the metal category. Okay? So that's why our mosts are there. We have one metal that is a liquid, and we have one nonmetal that is a liquid. Last examples. This one's really tricky. You look at those, what do you see? Rocks, give me more than that. Phase, what's the phase? Solid. What's the only other observable that we can run off of this? They're shiny. So we look at this and we say, they're all metals. Okay, yes, they were solids too. Okay. What are they? Those of you may be guessing on leading questions. These are metalloids. What's going on with our metalloids? Metalloids, okay, or sometimes referred to as semi-metals, carry properties from both the metals and the nonmetals. Okay. Some of them carry more of the metallic characteristics, some of them carry more of the nonmetal characteristics. Where might we find these nonmetals? Because so far we've said, metalloids, so far we said metals are to the left, nonmetals are on the right. The exact place where they transition between being nonmetals and metals is our metalloids. It's right on that line. It would be really nice if our periodic table gave us said line so we could help see the difference between where our metals are and our nonmetals are, and potentially where our metalloids fall. Does our periodic table give us that? Yes. Depending on the version of our periodic table, the ones in our class give us a bolded staircase line. That staircase line is the division between metals and nonmetals. Okay. Are all of the elements on that line then metalloids? You can answer that question for me by looking at your book. Are all of the elements on that staircase then metalloids? No. Some of them are, some of them aren't. Okay? So if you really need to know that information, which you might in a future chemistry class, you would have to memorize the ones that are metalloids. Okay? Sometimes they stick in your head, sometimes they don't. Typically the higher up on that table, the more you've got to memorize. Lower on it, tend to not memorize them. So if you take a look at your textbook, it actually color codes. Your metals are purple based on the ones I'm seeing, and your nonmetals are yellow. Your metalloids are green. They're even further nice because what do they give you at the top of that? A key, or at the bottom of it, depending on what page you're looking at, a key telling you what those colors mean. Okay? Questions about our metals, metalloids, and nonmetals? Okay. I didn't think I jumped immediately to this. Oh, yeah, I did. Maybe. So physical laws. So now we come into the part of our chapter where we start talking about some laws. One of the big laws that came out was the conservation of mass. This is kind of a big deal, okay, as far as our science goes. What we end up defining is that matter, solids, liquids, gases, cannot be destroyed, okay, in a chemical reaction. So anything that has matter, I can't destroy it. I can change it. I can mutate it into a different phase. I can mutate it into a different compound. But the matter still exists. It does not disappear. Why might this be kind of an odd observation? Okay, let's take a look at a couple examples. We could go through and take hydrogen gas. We're not going to release it into the room because that would be mean. We could release hydrogen gas into the room. We could light a match. When we look at hydrogen gas, it's a gas. We don't feel it. It just kind of floats everywhere. And if we, boom, lit up the room and then cooled down the results, what would we end up seeing? Water. What's special about water? Water being that liquid phase, we tend to look at that and say that has mass. So I started with nothing that had apparently no mass, and now I have mass. So way back before the late 1700s, they're like, oh, we created matter. What they didn't realize is that we can get a mass of the hydrogen. It's not as easy to do, but we can get a mass of a gas phase. We could look at the reverse, which makes it a little bit more challenging. I can take wood, put a block of wood on the table here. Let's not do that. And I lit it with a match, and we just watched it burn. Eventually, what happens to the wood? It chars. Let's keep pushing. Let's burn the junk out of it.
It turns to ash.
Turns into ash. Compare the weight of the ash to the wood that you started with. It's a lot less. What did we just do? We destroyed matter. Wah! No, we didn't destroy matter. What we ended up doing is converting it into another phase. That other phase was a gas. Remember what we said about the previous example, our gas, not easy to measure. Okay? So this observation took a lot of time to be able to process and understand and fully say, okay, yes, we believe this. We have to run very careful observations of our reactions to predict and validate that this is true. What does this mean mathematically for us? Okay, and I'm actually going to erase the wood oxygen gas one because that's too complicated for me. We start with 1 gram of hydrogen. And for those of you that may know how to balance and do all those calculations, don't. Just take my word for this. We got 1 gram of hydrogen, 4 grams of oxygen. I react these with each other, and I convert it into water. Assuming I picked valid numbers for this, what is the mass of water produced? 5 grams. Conservation of matter. Okay? conservation of mass. I can't destroy that. I have to convert it all the way across. How do I know it's not converted into something else? That's what this equation is telling me. To make water, I need hydrogen and oxygen, period. How else could we use this? Oh, I changed my mind. I like that 4 grams. What's the mass of hydrogen that I needed to react? How do you know that? Right. What we are saying in this case is that the mass of X grams of our hydrogen, whoops, I need to fix that. Am I okay writing H for hydrogen? Just want to make sure you're okay with me abbreviating stuff. Plus our 4 grams of oxygen, but I want to abbreviate. Are we okay with the symbol O? Yes, conservation of mass says that X grams of hydrogen plus 4 grams of oxygen equals 20 grams of water. What do we do? Algebra, and we can solve for what our X is. I'm hearing some mumbling. Did I forget something? Okay, good. I didn't think I forgot it.
You're with the 4 grams of oxygen.
All right, so now all we have to do is subtract the 4 grams of oxygen from both sides. So those of you that shouted out 16 grams of hydrogen, good job. There's our answer. Make sense? That's what we're doing with conservation of mass. Okay? Questions? So what happens when we actually pull our elements together? Okay. So Proust was kind of involved in this a whole lot. These are not names that you need to have memorized. Proust observed oxygen reacting with other metals, and he started to make evaluations of those reactions. What products were formed? How much oxygen did he have to put in? How much of the metal did he have to put in? And what he ended up noticing is that the compounds he generated, or the new things that he made, always contained the same elements in a constant proportion by mass. This gets further adapted by Dalton. Okay? But let's change this around a little bit to make it a little bit more understandable, I think. We're going to avoid the mass, and we're going to kind of push into Dalton's theory a little bit to understand this. Okay, so let's pick a compound. Compound I want to pick is water. Okay. That is why I might pick water.
Because it's all freeze.
Because you know it, and in particular, what do you think that you know about water that I want to reference for this question? The formula for water. What is the chemical formula for water? It's hydrogen and oxygen, true, but is that the formula for water? It's H2O. Okay, meaning that there are 2 hydrogen atoms per 1 oxygen atom to give us water. So I've got a beaker of water sitting on the counter. I reach in and point to a molecule. What's its formula? Okay, I reach in and point to another molecule. H2O. Another one? Still H2O. Another one? H2O. As long as I have water, every single one of those individual compounds will hold this formula. Okay. This formula can also be kind of converted into mass, because these numbers, or the number here and the implied number there, refer to the number of the elements, not their mass. Okay. That is what this law is referencing. Okay, in what I think is a slightly confusing way. Kind of make sense? Okay, let's try this again. Is this way too slow? Way too fast? What is my name? Okay, so we got a baseline there. Way too slow. Way too fast. Well, let's try it again. What was my name? Mike. Okay, we got a response. Way too slow. I'm getting some yeses and nos. Okay, so we're doing okay.
Just right.
You guys are just staring at me blankly and nobody seems to be writing anything. Like, why put all this effort in? Why aren't you writing? Okay. How can this be measured? This gets a little bit fun. I'm not testing you on this. I just want to give you an idea of what's happening. There are certain compounds that are relatively easy to break apart into their elements. And there are certain elements that are relatively easy to put together into different compounds. So what we can do is monitor those changes, and we can use those changes to predict something about the mass. So for instance, potassium chlorate, KClO4, when we heat that up, decomposes into two things: potassium chloride, KCl, and oxygen gas. Okay. I can entrap, weigh everything, and I can see the conservation of mass hold true. Okay. We can do the same thing with hydrates. There are certain compounds that will react-ish with water to trap water in the crystal lattice. That's known as a hydrate. What happens when we heat up water? Boils. Ultimately, it's turning into a gas. Well, if our compound is a solid and water is a gas, are they stuck together anymore? No. So we can see that change in mass as well. Okay, so there's a variety of ways that we could potentially test for these things. Okay. As far as being useful, we're starting to interpret ways to calculate different numbers coming out of things. Dalton took this a step further, and we'll again look at this later in the semester, and he came up with some rules behind how these things can combine and what these different pieces meant. Okay. So as a nice little added benefit on the right here, what do we have at the very top? If you look really carefully, 1 through 20. Yeah, one of those does look like a sun. Any idea what that is, 1 through 20?
The first 20 elements.
The periodic table of the elements. Okay? So we can be very thankful that somebody else came along and changed our elements into letters, symbols, as opposed to having to deal with all those fancy little shapes. Because to make a compound, say a complex compound of 20 different things, you got a lot of drawing to do. Okay? So Dalton ultimately took this together and started to build a better theory on what is happening at that very, very tiny scale to produce all of these different results. So, periodic table. We already talked about solids, liquids, and gases, metals, nonmetals, and metalloids. Okay? Let's push to the solids, liquids, and gases. Which of these are solids? I'll accept pretty much any answer. Left side are metals, not necessarily solids. Remember, there was an exception. Most of them are solids. That's a good answer. Okay. Periodic table shown on the board isn't particularly helpful because it's not giving us phase information. What's shown on the walls? On our wall, all of the black ones are solids. Okay. We've got some extra information there. Okay. So an easier question may have been, which of them are liquids? Okay. So there's some people catching on because you're probably close enough to the periodic table to see the key. On our periodic table, the blue elements are the ones that are liquids at room temperature. In this case, it's just mercury and bromine. Which ones are gases? The one that's left over are red ones. So for those actually watching the video at home, I can go through and real quickly. There we go. Okay. So we now have some phase information buried within this. Remember, this is chemistry. What we've been talking about is looking at compounds and elements. And to do all of that, you notice I had symbols up there. And as I had the symbols up, you heard me read out not the symbols, but words. How did I know those? Guess what you get to do? Memorize. How many of those do you need to have memorized? All of them. Okay, since you suggested that, you can memorize all of them. And I will test you with the list in front of me because I don't have them all memorized. Okay. It's roughly the top half. Okay. There are some that are also important that don't show up in the top half. For instance, let's clear everything again. For instance, mercury is not in the top half, but guess what? You need to know mercury. What's another one that's not in the top half that you might need to know? Gold. Okay. Tungsten, I think, is technically on that list. Okay. There are some common elements that are fairly heavy that you need to know. So what defines that you need to know? It sort of comes down to my job. Right? Every instructor comes up with something different. Some instructors do insist that you memorize all of them. I think that's a bit silly, particularly for these. Okay. Anybody know what those U's are referencing? Unnamed. There are compounds that have actually been discovered. And if we compare periodic tables, you'll notice that they don't match up. Because the periodic table I downloaded was older than the periodic table that's on our wall. Okay. Yes?
On this key, it says the U's are synthetically prepared. Does that mean that we made them?
Yes. So what I mentioned was black, blue, and red. If we look at our wall periodic tables, is that the only thing showing up on there? No, we've got the outlined elements. The outlined elements, as you just astutely pointed out, if we read really carefully at the key at the very bottom, it says that they were synthetically prepared. This means that some, actually, we're not even looking at ages here. They're probably okay as far as age. Scientists got together in a massive, massive facility and smashed atoms at each other to make something new. That is how those were made. So they were made by humans trying to get those. Kind of a neat process. So let's think about the likelihood that you're going to be asked to know any of those synthetically prepared ones. Not very common. Why? Because they aren't very common. We don't see them. The only place they show up is, in some cases, for split seconds, just enough time to observe that they came into existence and they immediately self-destructed. Okay? So some of those have existed as a single atom, which is incredibly tiny. Okay? And then immediately disappeared. Okay? Became something else. Okay, so you're not going to be responsible for those. What you're responsible for depends on every instructor. So what you will find online is this little handout that lists, anybody count really fast? Okay, we'll take that as a no. Something like 60-ish elements, you're required to have those memorized. What about them? The name, the symbol, sort of officially the spelling. Okay, you need to know those. So go on to Canvas, under, I think it's Helpful Files, download that and start memorizing them. How do you memorize? Horribly, if you're me. Note cards, flashcards, do whatever you got to do to try and get those memorized. You'll also notice, if we look really carefully, except this one isn't mine. I think I went through and adjusted this further. Can I get your help here real quickly? What else do you notice about those elements? Is there something different about one versus the other?
Some are bolded.
Some of them are bolded. Guess what the bolded ones mean? You really need to know those. Okay? Those show up virtually everywhere. If you don't have those memorized, you will guaranteed be losing points. The other ones, you may or may not lose points depending on the frequency that they decide to show up. Okay? I tend to test on just the bolded ones because I think those are most relevant. If you move through 151 and 152, some of the other ones will pop up. You got to watch out for them. Okay?
Do we test on numbers as well as the atomic mass?
Good question. Do I test anything about the numbers that show up on the periodic table? Indirectly, yes. But will you ever see a test that says for the letter or for carbon, what's the most relevant number, since we don't have the context of what those numbers mean yet, what's the most relevant number? 12.01, 26, 74.92, 18. I know I said those kind of fast. What's the most relevant number for carbon, which is our symbol C? 12.01, 27, 83. Can't see that, 8 or 10? Why 12.01? It's in that symbol box. So yes, you are ultimately responsible for it, but if you know where that element is, you will always have a periodic table that you can then reference. Why do you always have a periodic table? You have now been inducted into the Hall of Chemists. You are all chemists. Everybody carries a periodic table if you're a chemist. Okay. I used to have a little note card thing. In fact, some of you, well, you have me as your lab instructor. I don't have extra ones to pass out. Okay. Carry periodic tables with them at all times. Okay. I carry a periodic table with me at all times too, and it's not because of a note card, it's because I downloaded an app that has a periodic table in it, so I can look at it, find it at all times. Okay? That's why it's not relevant to have those numbers memorized. Make sense? Oh, they have one in the bookstore? Oh, cool. $4. You also find I'm cheap.
Less than a lot.
It's, yeah, it could, but more expensive than free. Okay, so periodic table, start memorizing those elements. Guess what might show up, say, the next time we meet? A little random quiz asking about some of those elements. Might be a good thing to start thinking about.
Do we need to know their atomic number or no?
You do not need to know the atomic number. That's the other numbers. Since we haven't officially talked about what those are, I'm trying to avoid using those terms. Compounds and chemical formulas. Anybody recognize this structure? Some people might not. You might even have seen coffee mugs with this drawing on it. I've seen a few people wearing t-shirts with this formula on it. What was that? Caffeine. It is caffeine. Okay. That's a lot of different stuff going on in there. Okay. That's a big mess. Okay. That's ultimately organic chemistry. We look at structure and all that fun stuff. We want to simplify that. How could we simplify that? We could drop it down to a formula. What do we mean by a formula? Well, I know there's carbon in there. How many carbons are there? I got 8. There are 8 carbons in there. I'm going to be a little bit obnoxious here. How many nitrogens?
4.
I'm trusting you. How many oxygens? Oxygens? 10? I don't believe you. Hydrogen, 10. We now have the potential for a formula. There's our formula, representing caffeine. That's what our formula tells us. We go through and count how many times that symbol appears. Does that tell me anything about the mass of carbon? No. Why not? If we look at a bicycle can be decomposed into tires and a frame, right? So if I look at 2 tires and the bicycle frame, does that mean the tires necessarily weigh twice as much as the frame? No. So mass does not necessarily correlate into our formulas. It's just the number of them. And it doesn't give us any information about density either. Okay? So we've got tons of formulas. H2O means? Fair enough. Good answer. Let's try that again. Composed of? 2 hydrogens, 1 oxygen. Take a look at C6H6O6. That was dumb. What is C6H6O6 composed of? Anybody recognize what C6H6O6 is?
Isn't it sugar?
It is sugar. Okay, it is glucose. Okay. Every single time is it glucose? Nope, because this doesn't tell us anything about the arrangement of those atoms. What is the carbon bound to? What is the oxygen bound to? What is the hydrogen bound to? If I change where those atoms are arranged bound to each other, even though it's the same number of elements, that does not mean it's the same compound. Okay? This is one of the reasons why formulas suck. And we avoid them in organic chemistry because we lose all understanding of what that molecule can do. And instead, what we do for Gen Chem, in an attempt to simplify things, we give you formulas because instead of having you look at how things can potentially react, we tell you it reacts, quantify it. And if you're dealing with numbers, you don't want to deal with structures at the same time. It makes things messy. Okay, so at this point, what we're asking you to do within Gen Chem is a lot of that quantitative observation. How much of this to do this to do this? Okay, not can it do this? Okay, so that's what our formulas represent. Any questions about what's up there? Anybody notice any trends? say in particular, if you think really carefully back to what I had just drawn up for a formula, do we notice anything interesting with those three? A lot of carbon, hydrogen, and oxygen. Particularly these two, what do you notice? What's it start with? Carbon, then it goes hydrogen, then it goes oxygen, and we got this weird thing, another hydrogen floated out there. Why is that hydrogen floating out there? We're trying to imply something about structure and formula all at the same time. What's happening with this one? Same deal. Why do we pull the hydrogen way out front? I'm trying to imply something about function as well as formula. So the exact, technically no, the exact order isn't super important, at least at this stage for our organic compounds. When we get into nomenclature, chapter 6, that's when we start talking about the proper order for things. At this point, don't worry about the order, worry about the numbers, where the numbers show up and where the symbols show up. Okay, or that the symbols show up. Questions on that? You like how I did that? I said questions and I moved to the next slide. Were there questions on that?
You're doing that a lot.
Okay. So, next big part, chemical versus physical changes. I personally hate talking about this right now, because what is the difference between chemical and physical changes? It is all about how different atoms are chemically linked to each other. How many of you know anything about a chemical linkage? Ooh, 2 of you. So this is a really good topic to bring up within the very first unit. It shows up in your textbook, we got to address it. Okay, so there's some things that we have to evaluate. For physical properties, okay, we're looking at phase transitions, particular colors, densities, solubility, conductivity. And that means as long as I'm looking at that same element and I don't change what it's connected to, it stays the same. Chemical properties, if I now change what that element is connected to. If I take water, which is just hydrogen and oxygen, but I now move to a different formula, H2O2, would I expect different properties, different physical properties for these two compounds? Yes, because I have changed the chemical properties. What did I change about the chemical properties? Extra oxygen. Okay? Read through the section on this on your textbook. We will be looking or starting with this when we start again, whenever that